So 15% grades you will get, I believe, easily, because I give quite a lot of time for the homeworks, like 1 week, and problems maybe like 10 or a little bit over 10 problems, but they are not that difficult. And some problems are MATLAB related. It's good that you should know MATLAB at this stage. And there are 4 to 5 quizzes. Total percentage which the quizzes covered are 25%. There are two tests in the midterm, 30%, and final project is also 15%. So it's a non-cumulative final exam. So you don't have to worry uh, all the previous chapters. I would just start from the usually the last few chapters. I will announce that what to prepare for the final exam. And final project comes from 15%. In that, it's a project which you will select with your own team member. I'm gonna announce the team members. What I will do, look over here, you see my screen. I will just add all these people, like 2 people per team. Does it sound good to you? Or do you want to have your own partner? It doesn't matter. At graduate school, it doesn't matter. Hmm? You want to find your own team member? Okay. So I was trying to explain you that 15% of the project, research project comes if you write on paper less than 10 pages. Don't go beyond 10 pages. It should be at least like 10 pages or 11 pages, not less than 10 or not more than like 10 pages, like 10, 11, 12, because I don't want you to write down a lot of stuff which will be difficult for me to get it published. I want to get it published. And did you have a chance to take a look at the announcement? I wanted you to make an account over the Overleaf, or you should. Do you know there is a software LaTeX, and you can use the account to generate the paper by the programming, and it's easy. But I would also prefer you to write down in Microsoft Word, since people can easily edit it in Microsoft Word. Is that okay if you use Microsoft Word? Okay, you can use Microsoft Word to write down your paper. So let me show you my paper, previous paper, paper one, Sabra, paper two. Suppose this is my paper about the broadband measurement of transitional and angular vibrations using a single continuously scanning laser Doppler vibrometer. So that was my research objective, to find out the linear and angular vibration from the vibratory media. And the medium I used gelatin. Let me show you. You see the gelatin? I bought it from like a public store or Kroger store, and made a gelatin and started tapping it and see whether my scanner can detect this vibration. So let me show you. Over here, this is, so the theory behind this paper revolves around the equations cosine and sine wave, and velocity is the linear velocity, and the angular velocity theta dot is the angular velocity, vz is the linear velocity, perpendicular to the plane. And then my experimental setup, these are the detectors, sensors. So I'm shining the sensors on a mirror, and the mirror is a scanning mirror which scans the surface of the gelatin, which I'm vibrating with certain frequency, broadband frequency, around 100 hertz. So when I tap it by 100 hertz, so gelatin media starts vibrating, because my objective was to detect the vibration on human muscles. So human muscles, they also vibrate when you contract your bicep, they start vibrating. But this is a scanning laser sensor which can detect the bicep vibration. But I'm first of all uh, putting the gelatin rather than putting human under the laser. Gelatin, I made it like a custard, custard. So it's like a custard, so you can just vibrate it and start vibrating. So you see, I was able to generate the vibration spectrum from 0 to 50 hertz. This is a linear vibration, and the angular vibration is modulated at a frequency of 200 hertz, theta dot x, theta dot y. And then I separated them using the signal processing technique, linear frequency modulation. You don't have to follow exact methodology, but at least this paper is very good paper for you to start working on an abstract. So 15% you will start it this week, next week, but you will submit it like before the end of the semester, maybe third last week or second last week. And every 2 weeks you can get a homework assignment to give me the continuous improvement in your project. First you will make your team members, and if not, next week I will just pick my own Excel sheet and pick up 2 people per team, and I will be the reviewer, co-author reviewer, that I'm reviewing your paper and see. And the project should be related with the vibration, like acoustics, vibration. Some people can have some knowledge from. I do have accelerometers in my lab for in-class students. You can come and visit my lab. I can gather some vibration data from the sensors I have in my lab. If you want to come, I'm here tomorrow at 11 o'clock in Q336. You can stop by, but I think you don't come on Wednesdays, right? But if you wanna come, shoot me an email. I'll open the lab for you, and I will show you the accelerometer. You can perform the vibration collection analysis. Once you collect the data on any vibrating media, then you can do the signal processing and do the result, just discussion results. That will be a nice paper. But what type of vibration research you want to conduct? Resonance. Resonance is not good for machinery, so you want to detect resonance. And how can you identify resonance? How can you save your machinery? This is one of the papers I published. And then I have another paper I'm sharing with you. There is another paper I wrote down in the and published in the Journal of Acoustical Society of America, and surface wave measurement using single continuously scanning laser Doppler vibrometer application to elastography. So that paper got published, and you see, I'm trying to see whether this single laser can also extract multiple locations vibrations. Maybe like in the span of 5 centimeters, like if you scan the 5 centimeter on your biceps, and then it can pick like 28 locations. I think it's 28. I just mentioned some. So rather than using 28 different sensors, you can just scan it using a mirror. I had a small mirror in my lab, which can which can rotate, which can also translate. It depends whatever signal I give inside the controller, it starts following that signal, and that was very helpful for me to scan the laser and collect the data. You see, I'm scanning on the biceps to extract the vibration which I'm generating intentionally. So this is an active vibration. It was very interesting. So I would suggest for in-class students, you can make your in-class groups. The people who are sitting here, you can work together. I think there are how many more students in the in-class? Let me check. So total 8 students. So you can make a group of 4 students. Two 2 students per team or 3 students. Should I allow 3 students or 2 students? What do you suggest? 2 students per team, good, makes sense. I'll be your third team member. Okay, let us begin our lecture. I was talking about so next week you will come up with certain at least 2 design ideas. What do you want to achieve in an abstract? I will share with you some of the examples that will help you what I have in my lab, and what if you don't access the lab like online students, how can they still publish paper without coming to campus collecting the data? But if they come to campus, that would be nice that they can use my lab to collect the data. And then the next task is, I think I showed with you over here. It should have been here in second lecture. Yes. I'm gonna upload these papers on the D2L for your help when you open the assignment Dropbox. Have you guys written some kind of report before your academic career, like student paper? Have you written some paper before? If you have not written any paper, but you still have the guidelines from my paper, introduction, theory, experiment, if it is an experimental based research, or if it is a review paper, it's also acceptable. And then collecting the data and discussion about the findings, that completes the paper. Any question? The online students.
Also,
Yes. This is very blurry. The topic which we are going to cover is chapter 1, some of the missing topics. So let me show you this. Please write down this formula. The sine wave or cosine waves, they are the simple harmonic motions which have certain radiant frequency, which is omega. Omega is defined as the natural frequency. Okay, so how many radians per second the system covers, and or the resonance. Another name is natural frequency. So omega has been defined as this. So it's a time domain. Omega can also be written like this: 2 pi f. And the time period in our book, time period is represented by letter P. If you see, this is letter P. Okay, so time period in our book, it is letter P, which is like a, if this is a wave, so the time to complete one wave, it is the time period. And time period is the inverse of the frequency. And I mentioned here omega is radiant frequency, which is 2 pi f. And f is omega over 2 pi. And if I take the inverse of f, which is period 2 pi over omega. So this is the same formula written here closely. If you take a look closely here, 2 pi over omega. Period is the time between two adjacent peaks. So if you have a sine wave time period, if you, it is better to take peak to peak, but if not, you can take any point and the next cycle you should select the same point. So if you have a sine wave, a sine omega t, so what is the velocity? A omega cosine omega t. What is the acceleration? And the amplitude is the coefficient of sine. Coefficient could be a omega, could be a omega square, and could be negative a omega square. So if I if I tell you that this is my a, this is my displacement a, then a omega square maybe like this one is my a omega square. You see, the frequency does not change. Frequency is the same. For so it means time to complete one vibration would not change. Even for the velocity, for the acceleration, it would not change because it's same frequency. And it is also known as a single frequency, or we call it harmonics. You will see this word harmonics. Next, you can add, if you have multiple harmonics, you can add them. So I'm saying that for negative omega square, it would be flipping. This is my negative a omega square. So you should know these are the basics of the oscillations. And now I want to show you, this is the same explanation of the same idea. I did not use the leading phase, like cosine and sine waves. They are pi by 2 phase angle apart. So if the sine waves starts from here, then the cosine wave starts from here. And the phase shift between them, I will say this is the phase shift. It is pi by 2. So there is a good example which it is related with your homework. So when you go home, try to do this example. You know about the trig identity, sine alpha plus beta equals to sine alpha cosine beta plus cosine alpha sine beta is the same thing. A sine alpha is sine omega t, sine or beta is phi, and the same thing. So that expression can be simplified, and you can find out the solution. The magnitude is c, and c is a sine phi equals to c. So magnitude is a. Sorry, this magnitude is a. So a equals to b square plus c square Y equals to A sine omega t plus phi, where phi can be found using, like, over here, this part is B, this part is C. The phase shift can be found using this sine phi, cosine phi, and then you can find it out. Either phi can be found as cosine inverse negative 5 over square root 34. Or it's in degrees. Hmm. 150. Can you calculate in your degrees or radians? Let me change the settings in radians. So if I redo this, so I change this from degrees to radians, so it is in radians. The angle is 2.6 radians. Another concept is oscillation with the exponential amplitude. Please write down this formula. I want to talk about something about the time constant. So, what do you mean by time constant? Suppose if you have given an initial condition to any system, for example, one is the initial condition, and you will leave it and it will come back to the mean position slowly and steadily. So, when it hits 37% of the mean value, then it's a first time constant. So I would say this portion e to the negative t over tau. So if time equals to time constant, then e to the negative 1, how much would that be? Exponential function? About 0.37. Like if it reaches 37% from the mean position or from the initial condition, it comes back to, yes. Yeah, that's a important question. Look, over here, exponent negative 1. You should bring your time such that it comes to 37%. If t equals to tau, then exponent becomes negative 1. And that's the first time constant. And now, and the second time constant, let's do this. For the second time constant, for the second time constant, what is exponent negative 2? About, it goes to 0.13, like 13.5%. 0.135 at 2 times the tau value. So if it reaches that value, it has passed 2 times the time constant. That time has passed 2 times the time constant. And then usually the control engineer, vibration engineers, what we are trying to understand, they let it go for 4 times constant. Okay, like it comes back to 2% of the mean position. So don't worry, I will upload the PDF of this lecture. So now let me show you. If you take the 4 times the constant, 4 times the time constant, so exponent, let's calculate that. It should be around 2% of the mean value. So let's do it together. So I'm going to write down here exponent negative 4.018 means 1.8, about 2% of the mean value. If the system means could be mass or could be motor, and if you give initial condition to the motor by hand, if you give by hand certain velocity, or and then you leave it, once you leave it, it comes back to, it takes some time for the motor to come down to stop is the mean value of the motor. Then if you being an engineer, I'm looking at the time, 4 times the time which passes 4 times the time constant means 98% has been achieved, or like 98% of the initial value has been released. And if you have e to the 0 at 0 time, it is 1. You see, at 0 time, the mass or any systems is taking the first starting point, e to the 0. Let's do one problem. The problem is a particular function has a form y equals to a e to the negative t over tau, and y at time 1 second, 4.912, the amplitude, y amplitude is 4.912, at time 3 seconds, this is 3.293. You have to compute what is a and what is tau. Tau means the time constant. Okay, so let's do this. So you guys know that this is, if suppose y1 a e to the negative 1 over tau, because I'm substituting time equals to 1 second in place of small t. Have you understood what I'm doing here? So, and this is equation number 1, and that means this is y2 a e to the negative 2 over tau. Now can you calculate? Thank you. Yeah, can you do me a favor? Can you calculate A and T? You have A and T, or you have two unknowns, two equations. So I give you some time to solve for tau and A. You found the answer? Yes. Do you compare with my answer? I am getting A equals to 6 and tau equals to 5 second. Yes. He got the same. You got the same? So if I were you, I would do like this. Equation 1 divided by equation 2. That will eliminate A. Agreed? So let's do this. 4.912 equals to A e to the negative 1 over tau. Equation 2 is 3.293 equals to A e to the negative 3 over tau. A is cancelled by A, and this is a number on the left hand side. So I can do the math here, and let's do this. Left hand side is, what is that ratio equals to? 4.912 divided by 293. About 1.5. Okay, so now about 1.5 equals to e to the negative 1 over tau plus 3 over tau e to the negative, or plus 2 over tau. And if you take ln on both sides, because we want to bring down the exponent, take the ln on both sides. So if you take ln on both sides, what is the ln? 1.1, 1.5. So ln 1.5, it is 0.4. My computer considers log as ln. Can you verify in your calculator? Is it 0.4? That's good. So what is tau equals to? Tau equals 2 over 0.4. What's that? What is 2 over 0.4? I got 5 seconds. So that is a time constant. It gives me 5 seconds. Do you have the same answer? Yes, 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 yes. And if you have 5 seconds at the time constant, can you plug it in equation 1 or 2 to get amplitude? So let's do the I just pick this equation 1. Let's pick equation 1 to plug it in to find out amplitude. Okay. So equation 1 is equal to 4.912 A e to the negative 1 over negative 1 over 5. Agreed. So then we have to do some just rearrangement, or probably just do the same thing. I can write down here. Let me write down here. A equals to 4.912 divided by exponent negative 1 over 5. What happened? 6, yes. Yeah, it could be any number, seconds, microseconds, milliseconds. I'm just explaining that could be, it's unitless, but it should be time. Have you understood this problem? Have you understood this problem? This is a part of your homework problem. Let's do one more homework problem. The question is, if you were to sketch the plot of function y equals to 7e to the negative t over 3, would you be appropriate range for y and appropriate range for y and time? 0 to 7, because 7 is the maximum amplitude when time is equal to 0. E to the 0 equals to 1. So y starts from, it goes from 0 to 7. That is appropriate range for y. Can you suggest me? I just told you for vibration engineers, time constant. What is the maximum time constant we are interested in? Can you take a look? 4 times. Good job. So what I'm going to do here, I'm going to check what is the time constant. Look at this value. It should be 3 too. In the numerator, time should be 3 in order to get 1. So time constant is 3 from the exponent function. So time constant, I would say, is 3 second, whatever, as he says, could be millisecond, any other second. But time for a settling time, we call it as a settling time. Sometimes engineers say 4 times the time constants. So it is better to practice over 12-second long data. So the range or the domain, range we have already done that, or the domain or the range for the time goes from 0 to 12. That will clearly explain you the picture of the behavior. Let's do one more problem. Yeah, this time is 0, it is 7. And it has to come to 0 because the mean position is starting from rest. That ranges from 0 to maximum value 7. You got my point? Now from here, there are two pieces coming together. So two functions. One is time constant is 2. The other one time constant is 5. So I will pick the range or the domain for the maximum time constant value. Then I will multiply that maximum time constant by 4. So I will say the domain starts from 0 to, can you guide me? 20. Good job. 20. And y value, you just add this up at 0, at 0 time, 6 plus 12 is 18. So it goes like from 0 to 18 or 18 to 0. So this is how you will pick the range and the domain of the exponential function like this one. Let's do one more problem here. A motor rotates with a RPM 3000. So N is the 3000 RPM. What is the speed in radians per second? Omega. And how many seconds it takes to make one revolution? Time to complete one vibration is time period. So I'm going to find out the time period or the capital P. Let me show you. The formula for the capital P is 2 pi over omega, and formula for this omega equals to 2 pi and 2 pi f. F, how do you get from N to RPS? Revolutions per second is the frequency. Agreed? F equals to number of revolutions per second. Can you convert RPM to RPS? 3000 divided by 50 hertz, 50 cycles per second, also known as 50 hertz. Agreed? You guys know this very well. So can I write down here omega equals to 2 pi 50? What's that? 31 314. That's the radiant frequency. How many radians per second it has traveled in? If you have imagine this a circle, imagine a circle, 314 radians per second. That's a lot of high speed. 50 cycles is quite high. But anyways, what is P? Yeah, time period. And then that is equal to, do you get 0.02? 0.02? That's good. Okay, so you can do the other question. Let me do one more question here. So here we have to find out the values of B and C. As I mentioned, sine trig identity. Sine alpha plus beta equals to sine alpha, cosine beta plus cos alpha, sine beta. So can I write down 10 sine 3t plus 2 with this help formula? Sine 3t plus sine 2. Sorry, cosine 2. Not sine alpha cosine. Why am I doing plus sign here? Sine alpha cosine 2. Cosine 3t sine 2. Agreed? So you just distribute this 10 inside. So 10 cosine 2 and sine 3t, don't worry about it. That is equal. The remaining part is B. Agreed? And for C, cosine t is not included. If you compare this equation by this equation, this is equation 2, equation 1. So you can compare C equals to, what is that? 10 sine 2. And let's do this. So I can write down here. What is my B then? Negative 4.16, because I have to multiply this value by 10. Hmm? You can use formula sheet. And the good thing is that it's open book.
Professor, I have a quick question.
Yes.
Would you prefer if we like approximated, like for example, cosine 2, or is it okay for like a homework or an exam problem if we left it as like 10 cosine of 2?
You don't want to answer this into degrees or sorry decimals?
I mean, I went ahead and did this problem like a couple days ago, and I left it in terms of cosine and sine. I didn't know if that was acceptable or if we needed to go ahead and like plug it in and like get an actual decimal value.
I think you should be fine. Don't worry too much. It's I still give you full credit for that.
Okay, thank you, sir.
Okay, let's do one more problem. Actually, the main important thing is the methodology. If you understand the method, how to solve this, then I feel when I grade my students' exams, then if you are writing the equations, trying to answer, I still give you a lot of partial credit. Okay, as measured by accelerometer. So these accelerometer we have at the lab, so you can use them for your research project. Amplitude of the acceleration of a certain vibrating object is 0.7 g. So I'm gonna do here. So y double dot equals to I told you that this is minus omega square. This is the amplitude. You remember if I tell you that, so negative, you don't have to put the absolute this sign here. But let me tell you, if the vibration, simple harmonic vibration can be written like this: y dot equals to a omega cosine omega t, and y double dot is a minus a omega square sine omega t, and the coefficient of sine omega t, which is this one, that is the amplitude of the acceleration. And I can write down here minus a omega square equals to 0.7 g. That is given here, and the frequency is 10 hertz. Compute the amplitude of the object's displacement. So we have to find out a, and the amplitude of the velocity, a omega. Assume the motion in simple harmonic motion. This is the simple harmonic motion formula using g as 9.81. So it's very easy. So you can find out from here. Look, from here you can find out what is a. Can I write down like 0.7, 9.81 over omega square? And what is omega, by the, if you know f? Good job. You see? So you have found it. It's a refresher. Chapter 1 is a review of your old knowledge. You might have studied somewhere in the vibration class, but we are still doing it just to start as the first chapter. And it's a good start. And then I will skip chapter 2, and it's a dynamics related. I'll come back to dynamics later, but I will start chapter 3 next week, because I want to finish vibration portion first of all, most of the, then I'll come back to dynamics, or I will see what I can help you with. So can I write down omega equals 2 pi f here, 2 times, so can you do the math here and help your professor? So if I do the math here, and you can check, do you get 1.739 into 10 to the negative 3 meters amplitude? And for the velocity, the amplitude is a omega. You just have to multiply 1.739 into 10 to the negative 3 by 2 pi f, and you should be able to get 0.11 meters per second. This is the amplitude of velocity. You confirm it? Yani confirms it, and you confirm it. That's good. You confirm. I did not mark the attendance. So what is your name? Nemeka? Okay, that's good. So we have done a lot of problems today, initial level, but let me show you one next thing which you can go over at home. When you go, I have uploaded some YouTube videos. Please watch those video lectures, and I'm gonna upload a few more, so that you should, hybrid means that 50% lecture you will study at home. So we meet once a week. The remaining week I have uploaded some video, and you know that channel I have uploaded 50 videos for the whole course, and I'm still developing more videos for my students. This lecture I'm going to upload on YouTube again, so that people who could not make up today, they can go and watch the video for the lecture. Okay, so then comes the next small topic is Euler's form of complex number. Complex numbers can be written like e to the iota theta, and then you can linearize it, and iota theta, So this is the thing which is important I want to mention here, that yeah, this is the Euler theorem. So e to the iota theta can be written as the sum of cosine and iota theta, because the complex numbers means like this is the real axis, this is the imaginary axis or iota axis. I call it as iota axis, the imaginary axis. Okay, if you have selected a point here, so it is like a, this is my z, this is my theta. So the polar coordinates can be like, this is my x, this is my y. So I can write down z as in the form of x plus iota y, and z magnitude is x square. When you take the magnitude, don't worry about iota. Just take the uh, magnitude of iota component, which is y. Okay, that gives you the magnitude of the vector z, like a Pythagoras theorem, you see. And then there are certain formula. If you have, you can also write this down. And theta can be written like a angle z, which is tangent inverse y over x, and z can be completely written as this vector can be magnitude e to the iota theta. So if I have two complex numbers, I'm multiplying them, so the magnitude would be iota theta 1 plus theta 2. You have to add those angles. I can rewrite here in terms of um, rectangular coordinates like z1, z2. I will say this is the magnitude, and angle theta plus theta 2. Because when you multiply two complex numbers, the angles are added. When you divide two complex numbers, the angles are subtracted. E to the theta 1 minus theta 2, or you can also write down the same way I wrote down earlier, z1 over z2 e angle theta 1 minus theta 2. So this is just a review of the complex algebra which you might see in your homework problems. With that, I'm going to end this lecture and stop the recording.